Hello everyone, in this video we are just going to implement external interrupt in the microcontroller STM32F446RE. Let's get started. So as the first step, let us try to create the project for our microcontroller in the IDE Keil Microvision. Now I am just opening the Keil Microvision IDE. So here once the IDE is open, just click on the project tab and click on new microvision project for creating your new project, and move to the respective folder where you want to store your project in your local, and provide a name for your project right over here in the file name tab, and then click on save. And in the next consequent tab that is popping out, you just want to select the microcontroller that you are working on. So in our case, the microcontroller is STM32F446RE. Just type in the microcontroller name. I'm just typing in like STM32F446 in the search box, and here you can see you are getting the microcontroller that you typed in the search box. Just click on the plus icon near the microcontroller, and here our microcontroller series is STM32F446RE. Just click the plus near the STM32F446RE and select the microcontroller right over here inside that tab, and then click on OK. And in the next manage runtime environment tab right over here, you just want to select the CMSys driver and the startup code required for the microcontroller. So just click on plus icon near the CMSys right over here and check this code right over here. And after selecting this, click on the plus near the device and then click on the checkbox near startup for generating the startup files required for the STM32F446RE microcontroller, and then click on OK. You can see the project has been created right over here in the project pane. Just click on the plus near the target for revealing all the project files, and then right click on the source group and click on add new items to group source group 1, and here I just want to create my main.c file required for the project. So click on the .c format right over here and provide a name for your file that you are creating in the name search box right over here. So I'm just typing the name of the file that needs to be created to be main.c. Just type in main since we have already selected the extension to be .c, and then click on add button right over here for adding the main.c file to your project. Click on the plus near the source group 1. You can clearly see the main.c file has been created to your project. And as a first step, we are just going to create or write down our main function. So I am writing like int main of void. So this is the main function which will be containing the logical part of the program which needs to be executed in our microcontroller. And inside the main, I am just going to create the while of 1, which is the infinite loop of the program. So this while of 1 is nothing but a never ending loop or infinite loop or super loop, whatever you call it. This is an infinite loop which will be containing the logical part of the program which needs to be executed again and again until the microcontroller is stopped. And the portion of the program just before the while of 1 inside the main function will contain the configuration lines of the program which needs to be executed only once in the lifetime of the program initially. So there are two segments of an embedded program. One is the configuration segment and another one is the infinite segment. So in configuration segment, before the while of 1, we will be writing down the configuration lines such as, for example, configuring a port, configuring timers, configuring communication protocols, etc. Just before the while of 1, and Another segment is nothing but the logical segment, which needs to be executed again and again until the microcontroller is stopped. So that part of the segment or that part of the program we will be writing down inside the while of 1, which is the infinite loop of the program. That's all about the main function creation. And now I'm just going to add the header file required for the project. So has include of stm32f4xx.h. So we can either use this particular common header file stm32f4xx.h, or you can use another header file available which is particularly meant for this stm32f446xx.h, which is particularly meant for this particular stm32f446re microcontroller or any other stm32f446 series microcontroller. So I'm just going to use this particular header file which is available specifically for this microcontroller, and that's it about the initial configuration needs to be done in Keil Microvision IDE. So once you are done with the main.c source file creation and all the main function creation right over here, I just want to do some basic configurations required for interfacing the board to our microcontroller, that is the Nucleo board or any other custom made STM32 microcontroller based board to your PC. Just click on the options for target icon right over here and click on output tab in this particular window zone right over here and check this create hex file checkbox. That's it. Now click on OK. Save the configuration, and now let us start writing our logical part of the program as per our requirement. Now that the project for the microcontroller STM32F446RE has been created and the main source file has been created successfully, let us try to open the old program that we have already written in this tutorial series. So you can clearly see this is one of the old program that we have written, that is the LED blink program. So in this program we have just performed a blinking operation in the onboard LED that is connected to PA5 of the microcontroller STM32F446RE in the Nucleo F446RE development board. So we are just going to use the same program and we are going to implement the external interrupt configuration and also the interrupt subroutine function in the same program. And also we will be utilizing the same PA5 onboard LED that is available in the Nucleo development board. So let me just copy this code as it is and I am going to paste it by deleting everything in this main.c. So we have successfully pasted the LED blink program right over here. Let me just compile this program. You can see the program is compiling with 0 errors and 0 warnings. That means the program is working fine. And now let me just show you some of the steps that we need to follow for enabling the external interrupt in our microcontroller. So these are the steps that we need to follow for configuring the external interrupt in our microcontroller, whatever may be the pin that you are choosing or whatever may be the channel that you are choosing. So I have derived these steps for enabling and using the external interrupt in our microcontroller. So let me just open the user manual of the microcontroller. And I'm just going to copy this and I'm pasting it right over after this line above the while of 1. So we are just going to perform all these configuration steps just before the while of 1. And regarding the logical part right over here, I'm just going to delete all the logical part that is available right over here. I don't want it, so or I can just comment it out. I don't want any of these. So here you can clearly see until here we have just enabled the clock for the GPIO port A, and we have configured the PA5 pin as output pin, and we have built a logic for blinking the PA5 onboard LED available in the Nucleo development board. And before this particular blinking process, we are just going to configure the external interrupt as per our need right over here. So I am just going to utilize the external interrupt of the PC13 pin. So PC13 EXTI we will be enabling, because so there is a user push button that is available in the Nucleo F446RE development board, and that particular user push button is connected to PC13 port pin of the microcontroller. So we will be triggering the external interrupt whenever that particular push button is pressed. So that is why I have chosen this particular channel, and we will be enabling the external interrupt for that particular PC13 pin of the microcontroller. That's it. You can clearly see this is the user manual of the Nucleo development board that I am using, and here you can clearly see that to the PA5 pin of the microcontroller the user LED is connected, and this particular B1 user push button is connected to PC13 of the STM32 microcontroller. That's it. And that particular push button is nothing but this blue color push button right over here, and this black color push button is the reset button of the microcontroller. That's it. You can see this B1 push button is the user push button which is connected to PC13, and this LD2 right over here is the user LED which is connected to PA5 of the microcontroller. So we are just going to configure this B1 user push button as external interrupt pin, that is PC13 as external interrupt pin, and we will be configuring this LD2, that is PA5 of the microcontroller, to which the LED is connected as output pin for demonstrating the external interrupts. That is, whenever external interrupt is triggered via PC13, we will be just toggling the state of the LED, that is LD2 or the PA5 pin of the microcontroller, for demonstrating the external interrupt. So this is the simple logic that we are going to build. So let's move to the configuration segment of the program. That is, we are just going to configure the external interrupt for that particular PC13 pin. So as the first step from the derived steps, you can clearly see we just want to enable the mask bit for the interrupt. So this particular mask bit for the interrupt is available in the interrupt tab of the user manual. So just click on the interrupts and events tab right over here in the user manual of the microcontroller, and in this particular chapter, if you move to the registers, the first and foremost register is the interrupt mask register, that is EXTI IMR. So this EXTI IMR is a register which is useful for enabling the mask of the interrupt. So here you can clearly see there are various bits available. It is a 32-bit wide register. Starting from bit 0, it is having till bit 31. You can clearly see bit 0 till it is having bit 31. And if I want to enable the mask for a particular pin, let's say to be PA0, PB0, PC0, etc., I just want to set the bit 0 of this register. You can clearly see 1 in any of the bit means interrupt request for the line X is not masked, and 0 in any of the bit means interrupt request for the line X is masked. So we just want to set the particular bit as 1 right over here. So let me just select and set the bit number 13, since we are going to utilize the PC13 as interrupt pin in our microcontroller. So I am just going to set the bit number 13 in this particular register with the help of pointer for EXTI. So pointer for EXTI is nothing but exti, that is external interrupt, and I'm going to point to the register IMR and I'm going to set the bit number 13 in this register. And as the next step, we just want to set the trigger configuration for the external interrupt. So this particular push button right over here on the development board is configured in pull-up logic, which means we have already studied in detail about two different button configuration. One is pull down and pull up. In pull up logic, initially when the button is not pressed, it will be having a high state. The microcontroller pin will be having a high state, and whenever a button is in pressed state, the microcontroller pin will read a low state. That's it. When the push button is in released state, we will be having a high signal, and whenever the push button is pressed, we will be having a low signal. That's it. That's all about the pull up logic. So here I just want the interrupt to be triggered whenever the push button is pressed. So whenever a push button is pressed right over here on the pull up logic, we know we will receive a low signal. So we will be triggering the interrupt whenever a falling edge is occurred in the particular interrupt pin. So pull up logic means whenever a push button is pressed, we will be receiving a low signal. That is, the signal transition will be from high to low. So we want to configure the interrupt to be occurring at every falling edge at the interrupt pin. But when I configure the interrupt to be occurring at rising edge, what happens is when I press and release the button, then only the interrupt will occur, because it is configured in pull up logic. So then only we will get a rising edge pulse in the particular pin. So here I want to configure this particular interrupt to be occurring at falling edge, since the button is configured in pull up logic, and also I want the interrupt to be occurring at every button press or as soon as the button is pressed. So for that you can move to the register called FTSR. So falling trigger selection register is useful for selecting the falling edge trigger method in the EXTI, and we want to set the particular bit number as per the pin number that you are configuring. So as we did before, we are just going to set 1 to the bit number 13 in the register, since we are going to configure the interrupt for PC13 of the microcontroller. You can clearly see 1 in any of the bit means falling edge trigger is enabled. 0 means falling edge trigger is disabled. So EXTI FTSR are equal to 1 left shifted by 13. And also I just want to disable the rising edge trigger signal. So this rising edge trigger signal is right over here. Another register called RTSR, that is rising trigger selection register. In this register I just want to clear the bit number 13 for disabling the rising trigger event at the EXTI PC13. EXTI And as the next step, we just want to enable the clock for sysconfig controller. Since we are going to use the system configuration such as external interrupt or any interrupt in our microcontroller, you just want to enable the clock for the sysconfig controller. So this particular sysconfig controller is connected to APB2 bus of the microcontroller. So I have detailedly discussed about the architecture of the microcontroller. So in that bus configuration, in the tab right over here, you could have seen all the peripherals and all the respective buses to which the peripherals are connected. So from that table I just derived that this particular sysconfig is connected to APB2 bus. So I'm just moving to the reset and control chapter and moving to the registers of RCC. I'm just going to open APB2 ENR. You can clearly see from this register I am having a bit called sysconfig enable, which is the bit number 14. So if I want the clock for the sysconfig controller to be enabled, I just want to write 1 to this particular bit number 14 in this register with the help of RCC pointer. So RCC APB2 NR R equal to 1, let's shift it by 14. So this is a common step. You just want to enable the sysconfig controller for every interrupt that you are configuring, whatever the interrupt may be. And the next thing is you just want to select the interrupt source. So that can be selected in the sysconfig chapter. There is a register. So just click on the sysconfiguration controller right over here. That is system configuration controller right over here, and move to the registers of system config controller. And you can clearly see there are various registers available in system config. Sysconfig mem RMP, sysconfig PMC, sysconfig configuration register 1, external interrupt system configuration register 1, external interrupt system configuration register 2, register T, register 4. So when I move to register 1, you can clearly see this particular register right over here is meant for EXTI 0, EXTI 1, EXTI 2 and EXTI 3. And when I move to, and regarding the description for this particular 4 bits, you can clearly see. So when I move to the external interrupt configuration register 1, that is sysconfig EXTI CR1 register, you can clearly see the upper 16 bits of the registers are reserved, you cannot write anything to it, and lower 16 bit registers are meant for configuring the EXTI. And each channel can be configured via 4 bits. That is, you can clearly see EXTI 0 can be configured via bit 0 to bit 3, and EXTI 1 can be configured via bit 4 to 7, and EXTI 2 can be configured via bit 8 to 11, and EXTI 3 can be configured via bit 12 to 15. So configuration goes like this. You can clearly see whenever I write 0000 to any of the 4 bits, let's take the bit to be bit 0. If I am writing 0000 to bit number 0 to 3 in this particular register, the PA0 pin of the microcontroller will be configured as interrupt pin, or interrupt for PA0 is enabled. And if I write 0001 in the same bits from bit 0 to bit 3 of this register, PB0 will be configured, that is PB0 external interrupt will be enabled. And when I write 0010, PC0 is enabled, and when I write 0011, PD0 is enabled, and it goes on like this. And moving to the register 2 of the sysconfig, you can clearly see it is having the same structure as register 1, except that the bits from 0 to 3 are meant for EXTI 4, bits from 4 to 7 is meant for EXTI 5, bits from 8 to 11 are meant for EXTI 6, and 12 to 15 are meant for EXTI 7. And similarly, when I move to register 3, I am having the configurations for EXTI 8, 9, 10, 11, and when I move to register 4, I am having the configuration for 12, 13, 14 and 15. So in our case, I just want to configure PC13 as interrupt pin, or I just want to enable the external interrupt for PC13. So I just want to use the EXTI CR4 register, you can clearly see here only I am having EXTI 13 configuration bits. So when I write 0010 in place of bits from 4 to 7 in this particular EXTI CR4 register, I will enable the interrupt for PC13, that is external interrupt 13 for the port C of the microcontroller. So I just want to write 0010 to this particular EXTI CR4 register. So I just want to set the bit number 5 and I want to leave all the other bits to be 0 in this particular register for enabling the clock for enabling the external interrupt for PC13. So I'm just going to use the pointer for sysconfig, that is sysconfig, and I'm going to point to EXTI CR. So this particular EXTI CR register is available as a buffer in this particular CMSys file. So I just want to use buffers like 0, 1, 2, 3 for register 1, 2, 3, 4, etc. So since we are configuring the register 4, that is EXTI CR4, I just want to use the buffer number 3 since the buffer starts from 0. So from 0 we are having registers till 3. So totally we are having 4 registers. Since we are configuring the 4th register, I am just going to use the buffer value 3. I am going to set the bit number 5 in this register. And as the next step, we just want to enable the interrupt for the microcontroller. So this interrupt functionality is particularly done via ARM processor directly, not particularly based out of any microcontroller manufacturer. So there is a standard APIs for enabling and setting priorities for interrupt. So we will be using that. So I can write like NVIC enable IRQ, and you can enable like EXTI 15 to 10 IRQN. So these are standard macros that is available by default in this microcontroller or particularly in the SkeelMicrovision IDE. So you can use this particular APIs and macros for enabling the interrupt, whatever interrupt that you want. And for setting the priority also, we will be having some NVIC, that is nested vector interrupt controller API. So set priority. So this particular set priority function receives two particular parameters. One is the interrupt that you want to configure, EXTI 1510 IRQ, and the second one is the parameter which is useful for setting the priority number. So let me just set the priority for this particular interrupt to be 15. So lower the value that you are providing as a second parameter, higher will be the priority of the interrupt. So according to your need, according to your application need, you can set the priority for various other interrupts. So that's all about the configuration for interrupt that needs to be done. So we have successfully configured the external interrupt required for the microcontroller, and now let us try to implement the interrupt subroutine function. So now you may have a doubt, what is the name of interrupt subroutine function that I want to provide? So I will show you a shortcut method for finding all the interrupt subroutine names or interrupt service routine names in your microcontroller. Just click on the plus near the device right over here and click on startup. In this startup, you can clearly see there is a default handler proc, and under this we will be having every interrupt subroutine function names. So these are all the interrupt handler names that is available in our microcontroller. So we are particularly using the EXTI 10 to 15 IRQ handler. So here you can clearly see we are having EXTI 0 IRQ handler, 1 IRQ handler, 2 IRQ handler, 3 IRQ handler, 4 IRQ handler, and here we are having EXTI 15_10_ IRQ handler. This is the interrupt subroutine name. So I'm just giving the name for this function to be EXTI IRQ handler. So since this is the interrupt subroutine function, you no need to worry about the declaration of function. You can directly write it below the main, and this will be called automatically by the processor whenever the interrupt is triggered. And inside this interrupt function, the first and foremost thing that I am going to do is I am just going to give a debounce timer. Let's take it to be some rough value. Since we have already written the loop delay right over here, I am just going to give a debounce timer, and suddenly after it I am just going to check for one interrupt occurrence bit. So let me just open the interrupts register again, and in this interrupt register we are having one register called pending register. So this particular pending register is useful for detecting whether the interrupt is occurred. So whenever this particular bit, let's take our case itself as an example, whenever the bit 13 in this particular register is set, that means selected trigger request has occurred, that is the selected interrupt has occurred. And whenever it has occurred, we will be just clearing the same bit by setting the bit. So you cannot clear the bit by software. You can clearly see this bit is cleared by programming it to 1. So we will be checking for the state of this particular bit number 13, since we are triggering the interrupt via PC13 of the microcontroller. We are just checking for the bit number 13 status. If it is high, we will be clearing the same bit by writing 1 to the bit number 13 in this register. So this needs to be done when you are working with various interrupts. If you are working on various 2 or 3 interrupts, you may be finding it difficult to identify from which the interrupt is triggered. Since you can clearly see this particular handler is meant for EXTI 15 to 10. So if you are enabling the EXTI 10 and 15, it is difficult to differentiate 2 different interrupts, because the same handler is called whenever both the interrupts occur. So in that case, you will be utilizing this particular pending register for identifying the interrupts. So I'm just going to call PR register, and I'm going to check for the bit number 13. So when the bit number 13 is high, I will receive a non-zero value right over here. Whenever a non-zero value is received in the if condition, this condition is true. So we will be clearing the same bit by writing 1 to it. And finally, the logic comes right over here. What we can do is we will just toggle the state of PA5 LED right over here inside the interrupt subroutine function. I'm just compiling this program. You can see the program is compiled with 0 errors and 0 warnings. So you can clearly see the logic is very simple. Whenever an interrupt is occurred, the program will be paused whatever it was doing right over here, and it will come right over here in the interrupt subroutine function. And inside this interrupt subroutine function, it will be checking for this particular interrupt has occurred or not, and if it is occurred, we are clearing that particular interrupt flag. And suddenly after it, we are just toggling the state of the PA5 onboard LED LD2. If it is low initially, we will make it high. If it is high initially, we will make it low. That's it. So this is the logic. Whenever we press the PC13 push button, immediately the state of PA5 LED will be toggling. If it was low initially, it will become high. If it was high initially, it will become low. That's it. So programming logic is also very simple. The program starts right over here and it will initialize everything done right over here. And after the initialization, it will move into this while of 1. We have written nothing inside the while of 1, so it will be ideally rotating inside this while of 1, which is the infinite loop. So whenever I press the PC13 push button, falling edge is detected in the PC13 and the processor will be interrupted by the nested vector interrupt controller via EXTI. So when that happens, the processor will be pausing whatever it was doing right over here and it will come to this particular EXTI 15_10_ IRQ handler interrupt subroutine function, and it will start executing all the lines that is available right over here, and once it completes everything here, it will resume back to the same place from where it left before coming to this IRQ function. So this is the process. This is the interrupt process, and the logic is very simple. Whenever I press the button, I will get the LED toggling via external interrupt. I'm just building the program again, and I'm just clicking on the options for target, debug tab, and settings. Make sure your Nucleo is connected properly, and in the output make sure this create hex has been selected. And now I'm just dumping this flash to the microcontroller Nucleo development board. The flash has been successfully downloaded to my Nucleo development board. Now let us try to visualize the output in the hardware. Now you can see this is my Nucleo development board. I'm just resetting the board. You can see the LED is turned on, that is the LD2 green LED is turned on, and whenever I press the user button, that is the blue button right over here which is connected to PC13, the state of the LED will be toggled via EXTI. You can see the LED is turned off. So this is the output which I got in the hardware. So I hope you learned the method for implementing external interrupt in our STM32F446RE microcontroller in this particular video, and also I hope you will be able to enable any external interrupt in this particular microcontroller or in this same series of STM32F4 series microcontroller. See you in the next video. Thanks for watching.